All right, engineering students, let us look at this topic on uh, on fuels. Um, we're just going to define fuels or fuel as a material that can be. Uh, People just know a fuel as something which can be burned, but you're going to see scientists have had to introduce a certain uh, definition, which means that it's a material which can be burned or altered to take into consideration nuclear fuels. Nuclear fuels cannot be burned, yeah? So they're just being altered. For example, uh, if you have uranium or plutonium, it's actually being changed. The atoms are being changed to some other atoms, and as a result of that one, the 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 total mass of the atoms plus the products that are going to be produced at the end, it is less than the total mass of the atoms plus the products which were there. I mean, the materials which were there initially, and therefore the difference in the mass results in the production of energy using the Einstein's equation. E energy is equals to the that mass which has been destroyed. Actually, it's been destroyed, multiplied by the speed of light, which is 3 times 10 to power 8, and then you multiply it by, and then you square it, yeah? So in this case, you're saying, yeah, you're actually destroying the mass, yeah? And then from the destruction of the mass, you're doing what? You are actually producing energy. So in this case, you're talking about a material. In this case, it's been altered, yeah? It's not being burnt. By being burnt, it means that it is being combusted like in oxygen to produce compounds such as carbon dioxide and water. Or if it may contain nitrogen, then there are those, uh, they're called NOx because for nitrogen it's a bit tricky. The oxides, you don't just get something like, even for carbon dioxide, you can even get carbon dioxide or carbon monoxide if there is the insufficient amount of oxygen. Carbon monoxide is produced. For the nitrogen, they are called NOx. It means that there is dinitrogen oxide, nitrogen oxide, nitrogen dioxide, all the different nitrogen oxides. So they're just being given the name of NOx. Then if you have sulfur, then there is sulfur dioxide, sulfur trioxide, and all those kind of things. So uh, uh, so you can be able to produce oxides of nitrogen, oxides of sulfur. Uh, but in general, I think and probably for the questions that you may be asked at this level of first year, may probably be compounds that contain carbon, hydrogen, and oxygen. Yeah, yeah. You may not be dealing with compounds that contain nitrogen and sulfur because the equation can be a bit complicated. Yeah, yeah. So, so in general, I think there is there's a lecture here on empirical and molecular formula, which is going to give you calculations on how you can be able to deal with if you've dealt with a fuel, it contains carbon and hydrogen, or it may contain carbon, hydrogen, and oxygen. How you can be able to determine the empirical and molecular formula, or you can be able to be just be given a compound. For example, you're just being told this is the structure. For example, you're dealing with something maybe octane. Octane is C8H18. You're just told uh, maybe like maybe like 0.5 grams of octane is burnt in oxygen. That's the information that you're given. And then you're told determine the amount of carbon dioxide and the water produced, and also the amount of oxygen that is required. Very simple, but from this uh, lecture series on empirical and molecular formula, you'll get the calculations for that. Yeah. Yeah. So it's very simple, and I think what I want to say is that this topic on fuels is one which I've given a lot of information. So this is the one which I'll take very little time because the notes are very detailed and it's got a lot of calculations. Let me just say, uh, over the years, I've taught this course on chemistry 2 for I think probably 12 years. Yeah. And I've got to say that it's not a leakage or whatever, but fuels, because they've got a lot of calculation from empirical to the which are going to be calling bomb calorimeter, plus the petroleum refinery. You're going to see that topics on fuels, they've been coming year in, year out. So there are topics which, in a way, you cannot be able to avoid. Fuels and what? IUPAC nomenclature. The other topics may be coming in one or another, but those two topics, if you're going to look at previous past papers, are they available in the library or wherever you get, they're talking about University of Nairobi Chemistry 2 papers. You're not going to fail to find questions dealing with calculations on fuel. So I really want you to be looking at the calculations on fuels and on this one on empirical and molecular formula. Yeah, it's just I think it's one of the first topics on your on the soft copy before you come to alkanes. So there's a topic on determination of empirical and molecular formula. That one is very, very important. So just to come to this one, as I mentioned, the soft copy of the notes are quite detailed, and uh, if I was to go to each one of them, even 3 hours may not be sufficient. Yeah, because fuels, there's a lot you can talk about. I'm really passionate about fuels, especially on the renewable energy side, uh, and particularly on biogas, which is biogas production from the organic waste. That's my research area. So I'm actually on energy, renewable energy, and the rest. And I can talk, I can talk even whatever. But yeah, there's a lot on that one. But the one which is indicated on the soft copy is just what is going to be in the area of what can be examined. So I'm not going to talk much about it, but just let me mention a few things. Just pointing here and there, but they're available in the notes. One of them that you is that you need to know that or the definition of what is renewable energy and the types of renewable energy. You're going to see that for the renewable, you're going to say that the process by which uh, it's going to be produced. You're talking about the life cycle. Is is uh, is what uh, is being produced faster than the rate at which it's going to be consumed. Yeah, but for the non-renewable, like for petroleum products and the rest, you know that it takes millions of years for the fossils, for the organics before they become fossils, and then they are compressed by the pressure and the heat of the earth to be converted into the petroleum. So the rate at which they are being, excuse me, the rate at which they are being consumed is faster than the rate at which they are being produced. So in that case, they are going to say they are not renewable. Um, so I think you may know about solar, uh, wind, and the rest. But something I may need to mention for the nuclear, you cannot say that. Okay, there is an element of the nuclear fuel which is renewable, but that one is not yet fully utilized. You're talking about something called nuclear fusion, to which you're going to get nuclear energy from the hydrogen and uh, from the hydrogen atoms. Yeah, in this case, you're converting hydrogen to deuterium and the rest. In this case, uh, you're fusing light atoms to form heavy atoms and with the production of energy. It's been made use of in something like a hydrogen bomb, but scientists are trying to make, rather than just make a bomb which will just go in a few seconds, they are trying to make something like a nuclear reactor which is based on uh, on the hydrogen atoms. It's still in the infancy, but once it works, then it's like you are reproducing the reactions that are happening on the sun. Yeah? All the stars, they make use of the hydrogen, I mean of the nuclear fusion. So you want to produce the reactions which are happening on the sun, but on the uh, I mean on the I mean uh, on Earth. Yeah, and as you know, the nuclear reactions, they they take temperatures of millions of Celsius, but there's no material which can go beyond probably 5,000 degrees Celsius. So they're making use of some other ways of using uh, uh, magnetism and other methods of trying to contain the heat within the container so that it doesn't cause the container to actually melt. Yeah. So, but there's something which is going on. So, nuclear fusion that is renewable, and the nuclear fusion like the one for like uranium and plutonium, that one is uh, non-renewable because once you exhaust the uranium and plutonium, that is it. Yeah, you may not be able to produce uranium, or you can be able to do recycling, but not produce sufficient uranium to be able to cope with the demand for the nuclear reactors and also probably regrettably even the bombs. Yeah. So for the nuclear energy, there is an aspect of renewable and there's also non-renewable. Um, there are many units. As engineers, you'll come to hear about energy, like the British BTI, British Thermal Unit, and the rest. But for this course, there are two units that you'll encounter, and in fact, a lot of books. Uh, though the SI unit is dual, but you're going to encounter a lot of books, either ancient or talking about old books or even current ones, in which the the unit of calories uh, is uh, is also being used. So in this case, I've just said 1 calorie is 4.184 joules. Because in this case, you can be given a question in which the unit for the fuels which is given in the question can be in calories, but you have to convert it to joules. Yeah. But if such a question occurs, you're going to be given that conversion in your question paper. So you won't be expected to memorize this. That 1 calorie is 4.184 joules. Now, once again, in the notes, I may, sorry for those who are taking petroleum, but once again, you'll get it in the notes. I would wish would have sufficient time to talk about coal. In this case, there are different types of coal: anthracite, lignite, bituminous, bituminous, and each one the various amounts of carbon and the rest, and the various uses for each. All of those ones you'll find in the notes. I do not have time to really talk about that. Once again, this topic on the fuel is well documented in your notes, and therefore I may not talk about that one. Now, petroleum comes from petrol, which means rock oil, yeah, petroleum, rock oil. Yeah? So uh, uh, scientists have just, or industrialists have tried to distinguish between petrol, as is called in Kenya, with in most of the countries in the world, petrol is just called gasoline. Yeah, so just to distinguish, yeah, with the petroleum. Excuse me. Excuse me. So petroleum is just means rock oil because it's found in the rock, and I think in the notes you'll see that uh, I think there are some illustrations which are showing how it is obtained from the uh, yeah, from the rocks, yeah. And once again, I would not want to really talk about this one, but it's basically a mixture of the petroleum alongside with the salt, yeah. So it needs to be uh, so there needs to be a way of separating the oil from the briner, and then uh, there are other things that needs to be done to the petroleum, like to try to remove some of the sulfur compounds, because before going to the distillation column, if you're going to have some of the sulfur compounds and they go to the petroleum product, like the petrol, then uh, when it's going to be burned, it's going to produce some toxic fumes, sulfur products, and therefore you want to avoid that one. So there are things that needs to be removed. Talking about brine, which is uh, which is uh, which is obtained when the petroleum is also obtained from the ground, and also sulfur, it needs to be removed. Yeah. Um, uh, Now in Kenya there's currently non-function. I think it's not functioning distillery at Changamwe. So currently, even if uh, the oil which is being produced in the Turkana fields, what happens is that it's actually being put onto the ships, uh, taken to where it's going to be refined. It could be in Saudi Arabia or in the Gulf, or whatever it is, and then we are buying refined product. Uh, the thing about refinery is that uh, if uh, if you're going to have a certain unless you have a certain amount of the petroleum being refined, you're not going to get profit. So there's something like a break even, as it's called in economics. So that's why it may be more expensive to put the small oil into your refinery. But if somebody else is going to be refining for a lot of people, then uh, the one who is refining for many people, then is going to get a huge margin of profit, as opposed to you. Uh, the, the equipment for the refinery is quite complicated. It's just, even if I'm just going to show it as fractional distillation, the process is quite complicated, and this one I've also put in the in the uh, in your notes, showing the exact distillation. Is quite a complicated process. I'm just trying to look at where exactly it is, but the refinery is quite a complicated process. Yes, there's the mirror process and the rest. Uh, so there this. So in the notes you're going to see a lot of, yeah, good. Yeah, so there's quite complicated about the petroleum industry. There is the distillation. Uh, which according to this one is, I think it's probably page 13 or 14 of your PDF. If you're going to be looking at that one, I don't know in what page, because there could be a different version of the soft copy of the notes which I sent, but they are complicated diagrams that are showing the exact refinery process. But what happens is that the crude oil uh, goes into a distillation column, and then the fractions which cannot boil are collected at the bottom, something like tar or bitumen, yeah. And then the ones which have got a very small boiling point, they are collected as gas at the top of the distillation column. So you're going to see, there will be gas like propane and butane. Then there are naphtha. Then there is the gasoline, as it's called, petrol. There is the kerosene, uh, diesel, lubricating oil, and the others. So in the notes you're going to see all that one, and I do not want to get into all that. I would have wished to incorporate videos as they are available over the internet, because this is something which is practical, but uh, but Google came up with a lot of rules that you uh, that before we actually upload a video, they must check that that the compilation that you are uploading does not contain any material which has been copyrighted by others. Uh, so that's why you're just seeing this video contains my explanation, but no other video or no other photo or any other thing which I may want to incorporate because of the copyright issues. But I think over the internet, if you're going to type fractional distillation, cracking, and reforming, you're going to get a lot of information, and you can get even the videos on that on the YouTube. And I mean, I do not have the power to really do that one because of the copyright issues, but you can be able to download uh, any of the ones which you want to see about fractional distillation. Cracking, it means that you've got a long chain of the hydrocarbon. You want to break it up under heat into smaller groups. And then reforming, you want to reorganize the chain, like the linear structure, into branch, to get something called, for example, if it's like something like the petroleum or the gasoline, you want to have one in which it it will not once it's put into an engine, it will not cause something called knocking or auto ignition. So there's something called octane rating for petrol, and then there is a C10 rating for the diesel fuels. So the one with the lower C10 rating, it means that it can cause rough engine operation. But for the octane rating, it means that one which has got an octane rating of close to zero, it means that it can destroy your engine by something called knocking. It means it is uh, premature ignition. Yeah, premature ignition, auto ignite. Yeah. So in the notes, you'll also see a topic at the end on calorimetry. Once again, I mentioned that these are things which are examinable, and will be available to explain this. I want to see in this week, which is beginning around 10th, uh, to be able to see how we can have face-to-face revision on some of these topics, like on calorimetry and other things on the fuels. Yeah. So calorimetry is the measurement of energy, where it can be a solid or liquid or gas, where it is burned in an equipment called a bomb calorimeter. Here in the Department of Chemistry, we've got such an equipment, but we are trying to see whether they can get many equipment. But currently, we've got only one equipment, which is called a bomb calorimeter. The thing about that, it's called a bomb calorimeter. It's actually like a bomb, but it doesn't explode. But the compound that you want to burn actually explodes in oxygen inside this container. and then that energy that is produced by, as a result of that compound burning in oxygen, some of that energy is absorbed by the equipment. So so in this case, you must be able to either determine the the something called the calorimeter constant for the equipment, or you can be given, yeah. In this case, you can burn a standard compound. Before you burn your compound, you can burn a standard compound like benzoic acid, yeah, which gives a known amount of heat. That will help you determine the calorimeter constant for the equipment that you're dealing with. And then from there, you can now determine the unknown. In this case, you've got the heat produced by the copper that is being burnt, and you're saying it will be equal to the energy that is going to be absorbed by the equipment, which will be equivalent, which will be calculated by the calorimeter constant multiplied by the change in the temperature. Excuse me. So that if the rise in temperature will probably be 4 degrees or maybe 10 degrees, that rise in the temperature multiplied by the calorimeter constant, which is given by the calories per degree, then you'll be able to determine the energy in joules or calories, which is absorbed by the equipment. And then that equipment is normally surrounded by a known amount of water. So with this equipment for the MC delta T, where in this case mass is the mass of is the mass of the water which has been added. What you're normally given is that you're just told maybe you've got 1 liter or maybe 1.2 liters of the water. So in this case, you're going to assume the density as being 1.0. So if you're going to be given 1 liter, you're going to say that the density is 1 gram per centimeter. So 1 liter will be equivalent to 1 kilogram. So M will be 1 kg. Yeah? You are going to make that assumption that the density is 1, and but for water the density is 1 at 4 degrees. Yeah. Yeah, but we just make use of that assumption. C is the specific heat capacity of water. Yeah, specific heat capacity of water, and if it will be in an equation, you're going to be given the value of C, and then the rise in the temperature, it's going to be the final temperature minus the initial temperature. That will give the delta T. So that will give the energy that is absorbed by the equipment. Yeah, I mean by the water. And then you've now determined the energy which is absorbed by the equipment. So that will give you the energy that has been released by the substance that has burned. In this case, if it's unknown, you'll just say, hey, that compound is going to produce this amount of energy. How is this thing related to you as engineer? You can be able to be producing new fuels like what? Like what some people have done is to produce maybe different types of charcoal, like from coffee husk or whatever. It can be coconut or anything that you can be, which you can be dealing with. You try uh, to make it like charcoal. Excuse me, in a limited amount of oxygen. Excuse me, to be able to make it black, and then this one is the one which you can be able to put in your equipment. In this case, you do not know, you don't need to know about the structure, but sometimes you can be in this case, the amount of energy, it will be kilojoules per maybe kilogram or kilojoules per gram, or maybe megajoules per kilogram or megajoules per gram. But there comes a time when you can be burning a substance of which the structure can be known. For example, like for petrol, in this case, you can be assuming that the petrol is an octane. So an octane is C8H18. Yeah. So in that case, um, uh, from the amount, I mean from the weight which which has been put onto the one which is going to be burning, you can be able to, from the relative molecular mass, you can be able to determine the kilojoules per mole. Yeah. So the answer which can be asked can be in kilojoules per gram for an unknown compound, or it can be kilojoules per mole for a known substance. And in the notes, in the soft copy of the notes, the I think they are giving cases whereby you can be given a known compound, so the energy which can be calculated can be in kilojoules per mole. Yeah. So you'll be able to look at all those things about the notes, and as I mentioned, this topic on the fields is quite large, and there are sections on the oil spills and also on biogas. As you know, biogas is not a fossil fuel, but it is produced by the decomposition of uh, organic matter in the absence of on the absence of oxygen, so that some of the carbon is not is not converted to the carbon dioxide, but it is converted to methane, CH4. Yeah. And then the one which is going to be burning will be the methane in the oxygen. So I think that's the much I'll talk about fuels. And once again, as I mentioned, it's just because of the time. So far, I've just talked for only 30 minutes. But if we were to get time, maybe later we may produce a video of hours and hours on the fuels. But for now, I think in these 30 minutes, the explanation which I've given will help you to really understand the soft copy of the notes. And once again, as I mentioned, please look at the internet, especially on the refinery process, and also coal. I think. Okay, let me just try to say. Excuse me. Um, uh, Excuse me. I think. Uh, Now, I've got something here. This is a substance of coal. Yeah, this is coal. I just want to see how, if I knock it with the metal, you see, it's actually like a rock. Yeah, and it cannot break like charcoal. Yeah, yeah. Can you hear the sound? And uh, though the hand may be a bit looking like dusty, so but actually like to me it's a rock. Yeah. So personally, I've got a sample. I wish you were in class, but maybe I'll be able to let you to look at a sample like this one. But this is a sample of coal. Once again, uh, uh, I think that's the much I'll talk about. I think I've got another substance of that was coal, and this is an example of something which I can call coke as a result of something called distillative distillation. Uh, it may look like there is ash, but it's still a rock. Yeah, can you see? It looks whitish. Yeah, still a rock. Yeah. So this is coke. Yeah, there is the coal which was black, and there is the coke. Each of these can actually burn. Yeah. Yeah. So okay. So I think. Uh, Once again, this is an exciting topic, but I hope the information that I've given you will be able to help you go through this course. But I believe for those of you who are doing the course on petroleum and also mechanical, will be able to look for more information. But what is contained in the soft copy and also in this video series is the one which will be examinable. It's examinable. fuels have got a lot of calculations. So I would rather you really know how to do the calculations. I hope by the end of this week I'll be able uh, to send you some revision past papers which contains questions related to chemistry too. So I think that's the much I'll talk about fuels, and I hope you've really enjoyed this short explanation on the fuels and also on the other two topics which I've mentioned on soaps and detergents and also on the polymers. Yeah. So thank you very much for listening. Okay.